Machine learning. You hear that term thrown around all the time, right? But what does it actually mean? Well, it's the tech that's recommending your next movie, it's powering your search engine. Honestly, it's a much bigger part of your daily life than you probably even realize. Today, we're gonna pull back that curtain and really dig into how this stuff works. So just think about this for a second. How does your phone's camera instantly find and focus on a face in a picture? For us, that's a piece of cake. We see a face, we know it's a face, simple. But for a computer, this is an incredibly difficult problem to solve. For the longest time, the standard way we programmed a computer was to give it a very explicit set of hand-coded rules. You'd literally write code that said, if you see this specific thing, then you do that specific thing. For face detection, you might try to write a rule like, if there are two circles next to each other, then maybe those are eyes. And this is exactly where that old approach just completely falls apart. See, a computer doesn't see a face. It just sees a giant grid of pixels, each with a different color value. That's it, a bunch of numbers. So how on earth could you write a perfect set of rules to define every single possible face in every kind of lighting from every possible angle? Well, you can't. It's basically impossible. So clearly we needed a totally new approach. And that's where supervised learning comes in. It's the most common type of machine learning, and the name itself is a fantastic analogy. Think of it exactly like a teacher showing flashcards to a student. We give the computer thousands and thousands of examples, but, and this is key, each one already has the correct answer or label attached. So here's how that process actually breaks down. First, you gather a massive data set of examples that have been labeled by a human. Step 2, you feed all of that data into a learning algorithm. And then, step 3, the algorithm crunches through all that data and builds its own internal set of rules. We call this the model. The key thing is, we're not writing the rules anymore. The machine is figuring them out for itself, just by looking at the examples. Now, let's just nail down a couple of quick terms here so we're all on the same page. In machine learning, each individual example, so like a single photo, is called a data point. And the different characteristics we use to describe that data point, things like pixel colors or image textures, we call those its features. Let's make this super concrete with a really powerful real-world example. Imagine we want to build a model that can predict if a tumor is cancerous or not. The input features would be all the pixel data from a medical image. And the output label, which would be provided by an expert doctor, would be either benign or malignant. By showing the algorithm thousands of these image label pairs, it starts to learn the incredibly subtle patterns that separate one from the other. Okay, but wait a minute. This brings up a really crucial question. How do we know if the model actually learned to see those patterns, or if it just, memorized all the answers we gave it? I mean, if a student just memorizes the answers to a practice test, they haven't really learned anything, and they're gonna bomb the final exam. It's the exact same idea for a machine learning model. To solve this, we do something pretty clever. We take our entire big data set and we split it into two parts. We use the majority of it, usually about 75%, to actually teach the algorithm. This chunk is called the training set. And that other 25%, we lock it away and keep it completely separate. That's our test set. And this gets right to the heart of the matter. The only way to know if our model has truly learned anything is to test it on data it has never, ever seen before. That's what the test set is for. It's the final exam. So here's the perfect analogy, the one thing to remember. The training set is like all the homework, all the practice questions, all the study guides you use to prepare. But the test set? That's the final, unseen exam that truly measures how well you actually understand the material. And this all leads us to the ultimate goal, the whole point of supervised learning. We want our model to achieve something called generalization. It sounds a bit fancy, but all it really means is the model's ability to make accurate predictions on new, real-world data that it's never encountered before. But getting a model to generalize well? It is a balancing act. On one side, you have something called underfitting. That's when your model is just too simple. It completely misses the important patterns and does poorly everywhere. But on the other side, you have the much more common problem of overfitting. Overfitting is exactly what it sounds like. It's what happens when the model doesn't just learn the general patterns, it starts to memorize the training data, including all the random noise and weird little details. It becomes so perfectly tuned to the practice questions that it can't answer anything else. This chart lays it out perfectly. As the model gets more and more complex, that's the line along the bottom, its accuracy on the training data it's already seen, that dotted line, just keeps going up and up. But look at the solid line.
That's its accuracy on new data. It rises to a peak, and then it starts to fall as the model begins to overfit. Our goal, always, is to find that perfect sweet spot right at the top of the curve.
So we've talked a lot about the process of supervised learning, but what about the algorithms themselves? It's really important to understand that machine learning isn't just one single magic algorithm. It's much more like a toolbox filled with all kinds of different tools designed for different jobs. And inside this toolbox, you've got a whole range of things. You've got algorithms like decision trees, which are great because they're easy to understand. Then you have the really powerful ones like neural networks, which are the engine behind what we now call deep learning. You've also got support vector machines, random forests, the list goes on, and each one learns in a slightly different way. And that really is the key takeaway here. There is no such thing as a one-size-fits-all algorithm. A huge part of the art and science of doing machine learning is really understanding your data and your problem so you can choose the right tool from the toolbox. So if we bring this all the way back to where we started, here's the bottom line. Machine learning is the fundamental shift in how we solve problems. Instead of trying to write impossibly complex rules ourselves, we curate data, and we let the machine learn the patterns and the rules on its own. It's an incredibly powerful way to tackle problems we once thought were just unsolvable. And this leads to one final and absolutely critical thought. We've seen that these models learn directly, one-to-one, from the data we give them. So what happens if that data isn't a perfect reflection of reality? What if it has its own biases baked in? A model can only ever be as good or as fair as the data it learns from. And that makes the quality of our data one of the single biggest challenges in this entire field.
Like and subscribe for more content like this.